This video is on finding absolute maximums and absolute minimums for a function. We'll start off by just taking a look at what defines it as a maximum or minimum, or an absolute maximum or an absolute minimum. So given f of x function over an interval I, alright, f of x has an absolute maximum at some value c if f of c is greater than f of x for all x in I. In other words, what we're really saying is that the y value is higher than all the other y values that you'll find on that interval for the function. That's what this f of c is greater than f of x means. F of x has an absolute minimum at x equals c if f of c is less than f of x for all x in I. In other words, when you evaluate the function at c, the y value you get is lower than all the other y values you would have for the function over the interval. And I'm just going to do a small sketch here just of what this might look like, just for an example. So if we have an x and y axis, and I was to draw this function here, maybe I'll draw it in a different color. Let's say we had something that looked like this. Alright, so this is some function f of x. Now we've previously talked about, relative maxes and relative minimums, and you can kind of see where they would fall. Relative minimum would be, here. They're at really the values of the function, right? So that's a relative min. This would be a relative min. And actually this little point here at the end is also a relative minimum because it's lower than the y values that are around it, right? Remember, we always do locally for relative, right? Sometimes they call them local minimums. And then we also have some local maximums, right? We have this relative max here, basically where all, the peaks are for your hills, right? The tops, this would be a relative max as well, because compared to the points around it, it's higher. And this would also be a relative max. So these are relative, like we talked about before, to the values around it. What makes it absolute, right? If you have an absolute maximum or absolute minimum, is if it's the highest point for the entire function or the lowest point. So when I look at this, if I was looking for the absolute maximum, well, where's the highest point for this whole function? Well, it's this last one here, right? So this point here is a relative max, but it's also going to be the absolute max. So this value right here, right, would also be the absolute maximum, because the highest y value we have, right? It's the highest value we have for the whole function. And where's the absolute minimum? Well, the absolute minimum is the lowest y value. Well, that's here, right? So this is a relative min, and it's also an absolute minimum, because it's the lowest y value we have for the whole function. So it doesn't have to be at the endpoints, right? This one just happened to be for the absolute maximum, but for the minimum, the lowest y value we had for the entire function over this interval was right here. So this would be the absolute min, because it's lower than all the other y values. That's what this really says. All right, so for absolute maximum, it's the highest y value for the whole function. For absolute minimum, it's the lowest y value. We have this theorem here, and this is going to help us in finding absolute maxes and absolute minimums. So the extreme value theorem says that if you have a continuous function f defined on a closed interval from a to b, so remember that means the endpoints are included. That's what makes the interval closed, right? When we say closed interval, the endpoints of the interval are included. It has to have, right? It must have an absolute maximum and an absolute minimum over that interval. In other words, if you're on a closed interval and you have a function that's continuous, there has to be some highest point and some lowest value. And that's what it's really saying. This is for a closed interval. That part's really important, right? So closed interval. For an open interval, we'll talk about that a little bit later. So to find the absolute maximum and absolute minimum for f of x on a closed interval, here's what we really do. Just when you find a relative max or a relative minimum, the first thing you want to do is find the critical values. So the first thing you want to do is find f prime of x, right? Find f prime of x and determine the critical values. Remember, this happens when the first derivative is either equal to 0 or when it does not exist or undefined. Then once you have that, this is where it changes a little bit. To determine if you have absolute maximums or minimums, what you do is you substitute in. This is important. You're not doing a first derivative test or a second derivative test. What you're really doing is you substitute in the critical values that you just found, right, and the endpoints, which are the a and b from our closed interval, into the original function f of x, and this will give you the y values for the function. So what you're really doing is you're looking to see, okay, what are the y values at all the critical values and at the endpoints, right? What are those corresponding y values? And then once you've done that, it's actually as simple as saying, okay, which y value was the highest? Well, that's the absolute maximum. Which y value is the lowest? That's the absolute minimum. And that's really what our steps are going to be. Let's take a look at an example here. So, for example, if I said find the absolute maximum and absolute minimum values of f of x equals x to the fourth power minus 8x squared plus 7 on the interval from -1 to 5. So first off, we know the extreme value theorem applies. We have a continuous function. We know it's continuous because it's a polynomial, and it's on a closed interval because the endpoints are included on that interval. So what do we do first? Well, our first step said, find the critical values, right? Determine the critical values. And to do that, we need the first derivative. So I need to find f prime of x for my first step in my solution. To find f prime of x, we're taking the derivative here. Derivative of x to the fourth is 4x cubed minus derivative of 8x squared. Let's bring the 2 times 8 is 16x. And then the derivative of 7 goes to 0. And then to find critical values, remember how that works. You set your first derivative equal to 0 or find where it's undefined. In this case, right, there are no values where it doesn't exist over this interval. Because on this interval, this is continuous. It's actually continuous everywhere. So we just want to set it equal to 0 and then solve for x. So 4x cubed minus 16x, first thing you want to do is factor out a GCF, which would be 4x in this case. And we're left with x squared minus 4. That's all equals 0. And then we want to solve this. Make sure you're solving this by factoring. We have 4x. This x squared minus 4 will be x plus 2 times x minus 2 equals 0. And now you want to find your critical values from here. Well, let's talk about our critical values. So 4x, you do have to set the x equal to 0, right? So 4x equals 0, or you could just say x equals 0 because you divide both sides by 4, but that's a critical value. Here we have x plus 2 equals 0, and here we got x minus 2 equals 0. And setting each of those equal to 0, when we solve these, here we'd subtract 2 from each side. So I get x equals -2. Here I add 2 to each side, so I get x equals +2. Now, once I have this, these are my critical values, but the only difference that we have from when we had a continuous function is that you have to look at your interval. The interval is from -1 to 5. If any of your critical values don't fall on your interval, then you just reject them. You don't use them because they're not on your interval. They're not part of the function we're talking about, essentially. So from -1 to 5, do any of these fall outside of that? Well, -2 does, so I'm just going to reject that because it's not on the interval from -1 to 5. I'm writing that out so you make sure you do that yourself when you're doing these problems. If you're not paying attention to this, you might use a value you don't need, and it could change your answer. So once you have that, right, now normally if this was just a continuous function we were talking about over an open interval, we would try to use the first derivative test or second derivative test. But here, to find the absolute maximum or absolute minimum, what we have in our instructions is just substitute in the critical values and the endpoints into f of x and find the y values. So this is actually different than what we normally would do, and it's actually easier to work with. So to find this, we only do this for absolute max and absolute minimums. We're going to substitute these values in. In other words, I need to find f of 0. I need to find f of 2. I need to find f of, so these are from the critical values, and these are from the endpoints, f of -1 and f of 5. And basically we're just substituting these values into f of x and determining the corresponding y values. So for f of 0, you have 0 to the 4th minus 8 times 0 squared plus 7, which you could probably see right away, that's going to be 7. F of 2, you would have 2 to the 4th minus 8 times 2 squared plus 7. And you can, do this on a calculator if you wanted to. 2 to the 4th minus 8 times 2 squared plus 7. I got -9 there. For f of -1, right? So those were the ones that came from the critical values. These are going to come from the endpoints. We would sub in -1 to the 4th minus 8 times -1 squared plus 7. This one here, -1 to the 4th is going to be 1. This is going to be minus 8 because that's going to be a positive. So 1 minus 8 is a -7 plus 7, so I get 0. And that's okay. 0 can be an answer. On f of 5, if you wanted to look at this one, we have 5 to the 4th minus 8 times 5 squared plus 7. I'll do that on the calculator. 5 to the 4th minus 8 times 5 squared is 25. Let's put 25 in there. Plus 7. This comes out to 432. Okay. So once I do that, all right, you got to make sure you remember why you did this. These are the corresponding y values for the function. Now when I look for the absolute maximum, absolute minimum, what I'm really looking for is the highest y value is the absolute maximum, all right, and the lowest y value is the absolute minimum. So when I see this, well, what's the absolute maximum? The highest y value I got is right there, 432. So this tells you that 432 is the absolute max, all right, and it occurs at x equals 5. So it occurred at the endpoint, and that's why you have to test the endpoints and the critical values in the original function. All right, and then what's the absolute minimum? We want the lowest y value. Well, the lowest y value we got is -9. So this would be the absolute min, right, is -9, and it occurs at x equals 2. So in this case, it occurred at one of the critical values. So that's how you know, right, what's the absolute max, what's the absolute min on a closed interval. You might see it written as ordered pairs, right? So you might see this same thing written saying the absolute min is at the point 2, -9. The absolute max is at the point 5, 432. Make sure it's a -9 there. So, it's actually different than what you would do if you were just trying to find the relative max and the relative min, because you don't use the first derivative test or the second derivative test here at all. But this is because it's on a closed interval. Let's take a look at just one more like this. So if I said to find the absolute max and the absolute minimum of f of x equals 16x minus x squared on the interval from -2 to 18. You might want to pause the video and try this one on your own. But it is the same type of concept. We have a continuous function on a closed interval. So I know by the extreme value theorem that there has to be an absolute max and an absolute minimum over this interval. And the way we find the absolute max and absolute min is the same way we start when we were trying to find relative maxes and mins. which is we want to find the first derivative so we can find critical values. So we're going to look at f prime of x here, and the first derivative here for 16x minus x squared, the derivative of 16x is just 16, minus the derivative of x squared is just 2x. And remember, to find critical values, you want to set that derivative either equal to 0, and you want to see where it's undefined, meaning it does not exist. Well, this is a polynomial, it exists everywhere. So we just want to set this equal to 0 and solve for x. For 16 minus 2x, you really can solve this, it's a linear equation. You subtract 16 from each side, and you end up with negative 2x equals negative 16. And then to solve, we'll just divide both sides of this by negative 2. And once you've done that, we get x equals negative over negative makes that a positive 8. And that's a critical value. Now make sure, does it fall in our interval from negative 2 to 18? Well, in this case it does. And it's the only critical value, right? So we got one critical value here, right? So CV for critical value. And that's okay. You can have only one. You could have none. You could have no critical values fall over your interval, and that's okay too. This is, the one that we got for this function over the interval from negative 2 to 18. And then what do I do? Well, if we're on a closed interval and we're trying to find the absolute max and absolute min, remember we just take the critical value, sub it into the function, right? So we want f of 8, and you take the endpoints and substitute them into the function. So we want f of negative 2, and we want f of 18, and our goal is to find the corresponding y values. So when we do that, we substitute in f of 8. This will be 16 times 8 minus 8 squared, right? Substituting into up here. And taking a look at that, we have 16 times 8 minus 8 squared. That gives us 64. F of negative 2 would be 16 times negative 2 minus negative 2 squared. All right, watch your signs on this. There's parentheses around that negative 2 getting squared. That other negative's on the outside of it. So you have 16 times, I really could probably do this out loud. 16 times negative 2 would be negative 32. This will be minus, this is going to be a positive 4. So negative 32 minus minus 4, it would be negative 36. You could do it on your calculator if you needed to. And here we got 16 times 18 for f of 18 minus 18 squared. And just taking a look at that, 16 times 18 minus 18 squared gives us a negative 36. So once you have that, remember the way you find absolute max and absolute min is the highest value you get is the absolute max. The lowest value you get is the absolute min. Well, what do we have? The highest value we have, well, we got 64. Alright, so this is our absolute max. The lowest value we have, well, it's a tie, right? Negative 36, and that's okay. You can have more than one that comes out the same, but since these are both the lowest value, this will be the absolute min. Alright, so the absolute max, just writing it out here, the absolute max is 64, occurring at x equals 8. In other words, it's the point 864 if you're looking for it on the graph. The absolute min, right, the absolute minimum is negative 36. So it is negative 36. And this occurs at, it's occurring at x equals negative 2 and at x equals 18. Or you could think of it as the points, right? The points we would have is negative 2, negative 36, and 18, negative 36. If you're looking for them as points on your graph. But remember, when we talk about the maxes and mins, either absolute or relative, we're talking about the y value is what makes it the absolute, or makes it the max or the min. Absolute means it's the highest value that your graph takes on, or the lowest. You know, if you were to sketch this out, this point would be higher than these points, right? These would be the endpoints actually in this one. So the endpoints would be your lowest points, and then this point would be the max at 864. Let's talk about what happens if you were on an open interval. So right now, we've only been talking about closed intervals. On an open interval, it is slightly different. Going back to our handout sheet with the definitions on it, we have this theorem here. It says, suppose that f is a function such that f prime of x exists on the interval I, which could be open or closed, and there is exactly one critical value, c, for which f prime of c equals 0. So just make sure we understand the premise. The premise is that if you take the first derivative and it exists on the interval that your function is on, whether it be open or closed, then if there's one critical value, right, that's what it's really saying. If you get one critical value over that interval, then if f of c is an absolute maximum at c, if f double prime of c is less than 0, f of c is an absolute minimum at c, if f double prime of c is greater than 0. What it's really saying is that you have an absolute maximum or an absolute minimum at that critical value if you do the second derivative test on it. And remember, second derivative test really said that, think about what this means. If f double prime of c is less than 0, right, that's saying that at that critical value, the second derivative being negative tells you that the graph would be, what, concave down. If you're concave down, since that first derivative was equal to 0 there, you know the slope is 0, this is going to be the absolute max. And here, similar but different, if you sub in that critical value and you get something that's greater than 0. So we already know that f prime of c equals 0, so we know that it has to be a horizontal tangent line. When we say this, right, f double prime of c is greater than 0, we're saying, okay, is this concave up or concave down at that point? Well, you know, f double prime of c being greater than 0 is positive, so it's concave up. If it's concave up, then that's the absolute min at that place where the horizontal tangent line is. It's a low point. So that's how the second derivative test really works and how it helps you here. So they don't say it explicitly, but you're really using second derivative test. We've done it before. This is what we did in the last section, actually. So let's take a look at a couple examples using this. So basically what it's telling us is that if we're on an open interval, or closed for that matter, but it's going to help us more on an open interval, if we get exactly one critical value, then that critical value is either going to be an absolute max or an absolute min, depending on if it follows which criteria for the second derivative test. So let's take a look. We'll do an example here. If I say find the absolute max and absolute min for f of x equals 8x plus 40 over x on the interval from 0 to infinity. So first off, recognizing that this is an open interval, so the extreme value theorem doesn't apply. It's not a closed interval. You can't substitute in endpoints. Open interval here, meaning the endpoints aren't included. So you still want to start the same way, though. You want to find that first derivative, because remember, what I'm really looking for is critical values. So for my solution, I want to find the first derivative of this. Before I can find the first derivative, though, remember I want to rewrite. All right, RW for rewrite here. We're going to rewrite f of x in a form we know how to take the derivative of. So we have f of x equals 8x plus, rewriting the 40 over x, I got to write that as x to a power. This will be plus 40 x to the, remember how you move it up. It was the first power, moving it up to make the exponent negative, so 40x to the negative 1. And now we're ready to take derivative f prime of x. Derivative of 8x is just 8. The derivative of a positive 40x to negative 1. The negative 1 comes down, which makes this negative 1 times 40 is negative 40x to the negative 2. Now, how do you find critical values? Well, the way you find critical values is either where the first derivative equals 0 or where it's undefined. Well, let me simplify this first derivative first, right? So we really have f prime of x is equal to 8 minus 40 over, when negative 2 moves the exponent, or moves the variable down the bottom, make the exponent positive. So you have 8 minus 40 over x squared. So remember, we want to talk about where this either doesn't exist, at which values, or where is it equal to 0. Well, we know that this does not exist, right? So f prime of x does not exist when what? Well, this can't be 0 in the denominator, so when x equals 0. So that would be a critical value normally, but make sure you look at your interval. Alright? X equals 0, is that on this interval? Well, this interval is open from 0 to infinity. It doesn't include 0. So x equals 0 is not on the interval, so we can, we need to check this and make sure we acknowledge it, but then we can reject it because it's not on the interval from 0 to infinity. So I don't have to worry about that being a critical value because it doesn't fall in the interval we're talking about in this problem. Remember, the other way that you have critical values is when the first derivative is undefined, or the other way is when it equals 0. So, or we set f prime of x, so 80 minus 40 over x squared equal to 0, and we want to solve that. Well, how would you solve this? The easiest way is probably to move this negative 40 over x squared over the other side by adding it to each side. So we end up with 8 equals 40 over x squared, and then multiply by the x squared to each side because you want to clear the fractions. So multiply by x squared. You also could cross multiply, put the 8 over 1. Gives you the same thing. We get 8x squared equals, these x squared cancel, so it just gives you 40. And then solving this for x, remember what you want to do. You want to divide both sides by 8 first. So I get x squared equals 40 over 8, which would be 5. And then, how do you solve that? Well, x squared equals 5, and you take the square root of each side. Make sure when you take the square root, you put plus or minus here. Alright, so we have x equals plus or minus the square root of 5, which is really two answers. Make sure you know that, right? It's x equals the positive square root of 5, and x equals the negative square root of 5. Again, it's okay to leave it, as a irrational number. Square root of 5 is the exact value, though. You don't want to give me a decimal here. What we want to acknowledge is, okay, our interval was from 0 to infinity. Do these both fall on 0 to infinity? Well, the square root of 5 falls between 0 and infinity, but negative square root of 5 is a negative value. It doesn't fall in the interval, so we can reject this one as well. Alright, so let's reject this because it's not on the interval, right, from 0 to infinity. So we're rejecting that one. So we actually only have one critical value. Right, so when we do this, we have one critical value, which is, x equals square root of 5. Now, according to the theorem we just talked about, that will make it either the absolute maximum or absolute minimum, depending on what happens with our second derivative test. So we have one critical value, and now we'll use. Alright, so now use the second derivative test to determine if that's the absolute max or absolute min. This is important that there's only one critical value, and that's why we can tell if it's the absolute max or absolute min right away. If it wasn't just one critical value, then we would have to work in a different way to find the absolute max or absolute min. So to use the second derivative test, we need f double prime of x. All right, so we need the second derivative, in other words. Well, what was the first derivative? The first derivative we had right here is 8 minus 40 x to the negative 2. The derivative of 8 would be 0, so I don't have to worry about that. The derivative of the negative 40 x to the negative 2. Negative 2 times negative 40 would give me a positive 80. And then x to the negative 3. Alright, so that's the derivative of the 8 minus 40x to the negative 2. And, we could rewrite this, in a simplified form as 80 over x to the negative 3 moves the denominator as x to the positive 3 power. And now remember how this works. You want to substitute in your critical value into the second derivative and then take a look at the sign on it. So we want f double prime of square root of 5. Right, that's my critical value. So f double prime is square root of 5. Well, this would be 80. This would be 80 over the square root of 5 cubed. And remember what I care about here. I only care about the sign. I really don't care about what the number is. 80 is a positive number. The square root of 5 cubed, well, that's going to be a positive number. A positive over a positive makes this whole thing positive. And that's really all I care about. Because if the second derivative is positive, that tells you your graph is concave what? Well, it's concave up. Concave up means it would look like this, which means that that critical value is going to be what? It's going to be a minimum. It's a low point. And if that's the minimum, since there's only one critical value on an open interval, we can say that's actually going to be the absolute minimum. That's what our theorem tells us at x equals the square root of 5. Alright, so we have an absolute minimum there because we had one critical value on an open interval. It tells you that if you have one critical value on an open interval, it's either the absolute max or the absolute minimum. In this case, it was a minimum. It's absolute because it was one critical value on that interval. And then make sure you remember, this is where the absolute min occurs, is at the square root of 5. We also have to go and find the y value that goes along with it, right? So how do we do that? We substitute back into the original function. So now we're going to find the y value. Find the y value that goes with it. We want f of square root of 5. And this equals, the original function, just as a reminder, was up here, is 8x plus 40 over x. So it would be 8 times the square root of 5, which would be 8 square root of 5. Plus 40 over x, so plus 40 over the square root of 5. And that's pretty exact form. If you were to try to rationalize this, let's take a look what would happen. This would be, you'd multiply this by the square root of 5 times the square root of 5. You'd end up with 8 square root of 5 plus, this would be 40 square root of 5 over, square root of 5 times square root of 5 is just 5. And then this equals, 8 square root of 5 plus 40 divided by 5 gives you 8 square root of 5. It actually ends up equaling 16 square root of 5. So your absolute min is 16 square root of 5, right? That's what this really tells us. That's the absolute minimum. Or you could say, the coordinates would be at square root of 5, comma 16 square root of 5. Right? So, it's okay to have irrational values, right? That's the absolute min. What about the absolute max? Well, there isn't an absolute maximum here. Make sure we should acknowledge that too, right? So no absolute max. Because the value we had for the one critical value is an absolute min, there are no endpoints to substitute in because this, is an open interval. You can't substitute in that 0 or that infinity. So there's no absolute max. Alright, let's take a look at one more here. So if we said, for this example, find the absolute max and absolute min values for we've got f of x equals x minus 1 to the third power. Now I didn't tell you an interval, so I'm just asking you to find it for that function. But the important thing to realize here is that if I don't give you an interval here, this is going to be a polynomial, right? So the third power. The interval is an open interval, right? It's an interval from negative infinity to infinity. So a lot of times that is our domain is an open interval that we already know. Right? In this case, our domain is from negative infinity to infinity. So because of that, you know that we're using an open interval. So that theorem that we just spoke of, if there's exactly one critical value, would apply as it becoming the absolute maximum or the absolute minimum. So the first thing we need, right, and it's essentially always the case, is I want to find the first derivative so I can find critical values. So we have f prime of x. Taking the derivative of x minus 1 cubed, you could expand this, but that'd be more work than you need to do. I would use a chain rule. Chain rule, remember, says take the derivative of the outside, so bring the 3 down in front, keep the inside the same. We have x minus 1. Reduce the exponent by 1, so you bring the 3 down, keep the inside the same, reduce the power by 1, and then you multiply by the derivative of the inside. The derivative of the inside of this, though, derivative of x minus 1, derivative of x is just times 1, derivative of that negative 1 is 0, so it's just times 1, which really means this is just equal to 3 times x minus 1 quantity squared. And then from there, right, once you have the first derivative, right, which we do, right, this is f prime of x, we want to find critical values. To find the critical values, remember you set the first derivative either equal to 0 or find where it doesn't exist. Well, it exists everywhere, right? This is continuous. There's no places where it's undefined. So we're going to set it equal to 0 and solve. Easiest way to solve this, I would divide both sides by 3, isolate the piece that's being squared, so you just get x minus 1 quantity squared equals 0. And then how do I solve this if it's squared? Well, you could expand it and then factor, but it's easiest to kind of recognize that, you can take the square root of each side here. Take the square root for plus or minus here, but plus or minus the square root of 0 is just going to be 0, so you end up with just x minus 1 equals 0. Another way of thinking about this, if you have a factor here to a power and it has to equal 0, the only way that can happen is if the inside equals 0, and that's what we have. And then we're going to solve this by adding 1 to each side, so we get x equals 1. All right, make sure that that critical value is on our interval. In this case, our interval is from negative infinity to infinity. It's an open interval, so it's going to be on there. And this is the critical value. Now, since there's only one critical value, we want to determine, is this going to be the absolute max or absolute minimum? So it says use the second derivative test to find out. All right, that's what this theorem says, right? If there's exactly one critical value, that's what we have. It could be the absolute max, or it could be the absolute minimum if it meets one of these criteria. So, we need to try the second derivative test. We need f double prime. So we need the second derivative. So f double prime of x, second derivative. Here's your first derivative, 3 times x minus 1 squared. Again, we'll use chain rule. Bring the 2 down, 2 times 3 would give you 6 times x minus 1 to the power, it will be the power 1 now, times the derivative of the inside, which is just 1. So this ends up equaling just 6 times x minus 1, which, this is f double prime of x. And remember what we want to do. We want to substitute our critical value into here and see if we get something that's positive or negative to determine if it's a maximum or minimum. Well, f double prime of 1, substituting in my critical value, is 6 times 1 minus 1, which is 6 times 0, which equals 0. So that's not positive or negative. So our second derivative test is inconclusive. That doesn't mean you stop. It really just means if the second derivative test is inconclusive, typically what we do is we use the first derivative test. So now use the first derivative test. So this will give us more information. So if I use the first derivative test, remember how that works. You're going to make a number line, and on that number line is the number line for f prime of x. And on that number line you want to put your critical values, which in this case we only have x equals 1, so we only have 1. And you want to test values in f prime on each side of 1 to determine if it's positive or negative there. So if I said I wanted f prime of, let's say, 0, it's probably the easiest to use, f prime of 0, we're going back and we're testing up here into this 3 times x minus 1 that quantity squared. So it'd be equal to 3 times x minus 1 would be 0 minus 1 squared. This ends up being 3 times, this is negative 1 squared. So it ends up equaling, this is 1, and then 1 times 3 is 3, so it equals 3. The important thing here, though, is that 3 is positive. Oh. Yeah, so you sub 0 into here. You have 0 minus 1 squared, which is negative 1 squared. This will be a positive 1 times 3, because you have positive 3. So at 0, the first derivative is positive. So everyone to the left of 1 is positive. That tells you that the original function f is increasing, remember, right? A positive first derivative tells you the original function is increasing. Testing f prime of 2, again, into 3 times x minus 1, the quantity squared, will be 3 times 2 minus 1 squared. Well, again, this is 3 times, it'll be 1 squared, just 3 times 1, which is 3. The important thing that I care about, though, is that it's positive. So then everywhere to the right of 1, f prime is positive, which tells you the original function f is increasing. So we're going from increasing here, and then it continues to increase after 1. So is that a max or a min? Well, no, because this goes up and then it continues to go up, right? So it just flattens out for a second and then keeps going up. So what that really tells you is that x equals 1, or at x equals 1, there is neither a max nor a minimum. So it's not a max or min, it's not relative or absolute. In this case, though, since we asked specifically about it, then therefore, right, these 3 dots mean therefore, there is no absolute max or absolute min. And that's okay, that can be the case. So the answer here is that there isn't one. We showed why. That critical value, though, was the only possibility for an absolute maximum or absolute min, right, on this interval. If you think about what this graph of f of x would look like, this original function f of x equals x minus 1, the quantity cubed, if you remember what a cubic function looks like, this is just shifted to the right one. So what really would happen is you would have a graph that, just showing it down here, this isn't part of the work, but just trying to show you why it came out to what it does. You would have this cubic function that does this kind of thing. So it flattens out, but it keeps going. So you don't have to graph it. I'm not asking you to graph it. I just wanted to make sure you have an understanding of why there could be no absolute max or absolute min. Because it goes downward forever on the left, goes upward forever on the right, and it just flattens in the middle. It doesn't, it doesn't dip at all. So there wouldn't be an absolute max or min here. There's also actually no relative max or min. So there's no absolute or relative max or mins with this function. So the key thing in this section, though, is to make sure that you know the difference between what you do on a closed interval for a function compared to what you do if you have an open interval, because they are different. On a closed interval, to find the absolute maximum and minimums, you find the critical values, and then you just take them and the endpoints, and you sub them into the original function and determine, what's the highest y value, what's the lowest y value, and that's your absolute max and absolute min. On the open interval, you're going to be hoping that you only get exactly one critical value, and that's your candidate for an absolute maximum or absolute minimum. Making sure you understand the difference between the two. The only other thing I would mention is you also want to make sure that your critical values are on the interval you're looking at. If they're not on the interval that you're looking at for your domain, then you can't use them as critical values in the problem.